In the problem of central force field, generally we are faced a problem where two bodies or two particles interact one another via a central force. For example, in case of planetary motion, you know that the planet and the sun attract one another by gravitational force, and gravitational force is a central force. So such a problem where the two bodies interact with one another via some central force, that is called actually a two body central force problem. And actually the main purpose of a study of the central motion in central force field is actually to deal with the two body central force problem. Okay, planetary motion is a very good example of the two body central force problem. But by a technique we are able to transform the two body central force problem into its equivalent, a single body problem. It is possible. So in this lecture our aim is to discuss the concept that how we can deal with a problem of two body central force in terms of dealing the motion of a single body. So this problem is called a reduction of two body central force problem to the equivalent one body problem. Okay. So to know that technique, how this problem will be explained or solved, let us consider a system of two particles which interact one another by some central force. In this figure you can see I have shown that there is a body which is of mass m1 and there is another body which is of mass m2. And consider that these two bodies m1 and m2 exert central force on one another. It means there is a mutual interaction between m1 and m2, and that interaction is a central force. We consider it. Okay. As I have told you that between the earth and the moon gravitational force acts, so that is a very good example of a two body central force problem. Now there may be another body which may exert forces on these two bodies. So for a general result I have also assumed there is a third body which is outside of this system. Here system means m1 plus m2. m1 and m2 forms a system, and this body of mass m3 we assume that it is outside of that system. So you may call this body of mass m3 as an external body. It is not a part of our system. Okay. And so whenever this m3 will exert a force either on m1 or on m2, that will be called actually external force. And when m1 and m2 interact one another, that force will be called internal force. Why internal force? Because you know m1 and m2 are the two different parts of the same system, and when a part of a system exerts a force on another part of the same system, such interaction will be called internal interaction. Okay. So now one thing I would like to clear here, that we have considered m1 and m2 is two bodies. But remember, in particle dynamics or in Newtonian dynamics, we always consider a body just like a point mass. So in this discussion too, although these two bodies m1 and m2 may have a finite size, but we will treat these two bodies just as point masses. So I have defined in this figure, you can see that the position vector of m1 with respect to the origin of our coordinate system is r1, and that of M2, it is R2. I have considered it. Okay. Now, if you want to decide the forces acting on this body M1, so let us consider that F1 is the net force acting on body of mass M1. Then what will be this F1? Actually, F1 will experience force from two sources. One source is M2, which exerts a central force on M1, and another is M3, which is also exerting a force on M1. But M3 is the outside object, and M2 is the object which is just a part of the system formed by M1 and M2. So force exerted by M2 on M1, let us denote it by the symbol F12. It means F12 is the force exerted by M2 on M1. This is internal force. And plus this outside body, that is M3, may exert a force on M1. Let us say this force is F1 ext. Ext for external. It means the total force, the resultant force exerted on this body of mass M1 is equal to F12 plus F1 external. Here, as I have told you, that F12 is the internal force. It is the force exerted by mass M2 on M1, and F1 ext is actually the external force, that is a force exerted by M3, which is an object outside of this system. So the force exerted by M3 on M1 is called external force. Okay. Now, if you want to write the equation of motion of this body M1, equation of motion means second law of motion. You know that according to second law of motion, the net force is equal to mass into acceleration. Let us say that acceleration of this mass M1 is A1, then this will be M1 A1. And you know that A1 will be equal to d2 r1 dt square. Okay, because its position vector at any time t, let us consider, is r1. So after differentiating this r1 two times, you will get the acceleration. And in dot symbol, you know this can be written as m1 r1 double dot. So this F1 is equal to this much, but F1 is equal to F12 plus F1 external. So let us now substitute that this will be equal to what? This will be equal to F12 and plus F1 external, and that will be equal to M1 R1 double dot. Okay, and you can see actually I have written these things here clearly. What you have learnt, I have already mentioned it here. So you can see that the net force acting on M1 is F12 internal. Here there is no need to write the superscript internal, because this internal force is understood. So I have dropped this ENT in the previous lecture, in the previous step. But you can write it if you want to write. You may write. So let us write it for clarification. INT. I am mentioning it here. Okay. Everywhere you have to write now INT. So let us see here. This force, the net force acting on M1 will be F1 equal to F12 internal plus F1 external. As I have told you that this F12 is the central force exerted by M2 on M1, and F1 ext, this is the force exerted by M3 on M1. M3 means outside object. Okay, and when we will apply the Newton's second law of motion, that is equation of motion, you know F1 will be this much, and that will be equal to M1 R1 double dot. So M1 R1 double dot, this will be equal to F12 internal plus F1 external. Okay. Now, as you can see this figure, we have considered that what is the net force acting on M1, and then you have written the equation of motion of M1. In the similar manner, you can write the equation of motion of the another body M2 of this system. When we will consider the motion of M2, it will also experience two forces. First force will be due to M1 and another will be due to this M3. M3 is the outside force. So it will also experience an internal force. We will denote that internal force by the symbol F21, and the external force exerted by M3 on this M2, and that will be denoted by F2 external. So in the similar manner, when you will write the equation of motion of the mass M2, what will be that equation of motion? With an analogy, you can see this will be M2 R2 double dot plus F21 plus F2 external. You may write here INT. For clarification I am writing, but there is no need to write it. So again write it here. As you know that this F21 internal, this is central force exerted on exerted by M1. Sorry, this is by M1 on M2. And F2 external, this is force exerted by M3 on M2. Okay. Now, let us define a vector R equal to R1 minus R2. In fact, you can see if we treat this M1 as a point mass and this M2 also as a point mass, and relative to the origin of our coordinate system, if R1 and R2 are the position vectors of these 2 point masses, then the position vector of M1, if you write the position vector of M1 with respect to M2, then what will be that? That will be R equal to R1 minus R2. So you may interpret this vector R as the position vector or the radius vector of point mass M1 with respect to M2. Okay. So this R is defined by R1 minus R2. Now let us do a simple algebra. We simply multiply this equation 1. See here. This equation 1 is multiplied by, let us say, M2. This equation 1 will be multiplied by M2. And equation number 2, this is actually multiplied by, let us say, M1. Sorry, the page is sometimes turned, but this will be okay, don't worry. In every lecture, there is a certain time when the page is automatically turned, but it is not a bigger problem. So let us see. So what I was telling, we have to multiply equation 1 by M2 and equation 2 by M1. And after that, after multiplying equation 1 by M2 and equation 2 by M1, we simply subtract this equation 2 from equation 1. So I have written here like this. M2 times 1. It means you have to multiply equation 1 by M2. Minus M1 times M2. M1 times 2. 2 means equation number 2. Remember. So you have to multiply equation 1 by M2 and equation 2 by M1, and then we simply subtract from equation 1 to equation 2. So you can see in equation 1 there is what? In LHS there is M1 R1 double dot. You can see this equation m1 r1 double dot, and we will multiply it by m2. So this will be m1 m2 r1 double dot. Okay, and in the LHS of equation 2 there is m2 r2 double dot, and we have to multiply it by m1. So this will be m1 m2 r2 double dot. Okay, so when you will subtract, you can take m1 m2 as a common factor, and the remaining terms will be r1 double dot minus r2 double dot. This is very simple algebra. And again see, in the LHS, the first term in LHS of equation 1 is what? That is F12 internal. F12 internal. Okay? And you have to multiply it by M2. Multiply it by M2. And the first term in the RHS of equation 2, this is what? This is F21 internal, and we have to multiply it by M1. So this will be M1 F21 internal. Okay, F21 internal. And when you will subtract, you can see after subtraction, actually there will be, in fact, this much, m2 f12 minus m1 f21. Again I am writing here int for clarification. Okay, now see the second term in RHS of equation 1 and 2. In equation 1 there is f1 external, in equation 2 you can see this is f2 external, and after multiplication by m2 and m1, when you will subtract, this term will be m2 f1 external minus m1 f2 external. This is simple algebra. Okay. Now, as I have told you earlier that this m1 and m2 are mutually interacting with one another via a central force. So m1 exerts a force on m2. M1 exerts a force on M2, and that force is F21. And M2 exerts a force on M1, which we have considered F12. But this is just action-reaction pair. You know, M1 exerts a force on M2, M2 exerts a force on M1. So these two forces are simply action-reaction pair. And you know from Newton's third law of motion that action and reaction are equal in magnitude but opposite in direction. Okay, so from third law of motion you can say that F12 vector will be equal to minus F21. This minus sign actually indicates the direction. Okay, so in the first term in RHS of this equation, see here, which I am underlining, you can see we will write F21 equal to minus F12. And so this term will become plus, and our equation will be what? This will be m1 plus m2 times f12. You can take f12 as a common factor. Okay. Now, in the last term, see here, which I am underlining, you can see if you take m1 times m2 as a common factor, then what will be our result? Since in the first term there is only m2, but you have taken m1 also as a common factor, so you must divide f1 external by m1. Okay? And in second term there is only m1, but we have taken m2 also as a common factor, so we should divide it by m2. Okay? So our final equation after this simplification will be m1 m2 times r1 double dot minus r2 double dot equal to m1 plus m2 times f12. You may write here int internal plus m1 m2 times f1 external over m1 minus f2 external over a2. Okay. Now again we will do a simple algebra. Let us divide this equation both sides by this factor m1 plus m2. We have to divide the both sides of this equation by m1 plus m2. So in LHS there will be m1 m2 divided by m1 plus m2. In RHS, in first term this m1 m2 will cancel out, and in the last term again there will be m1 m2 divided by m1 plus m2. This is a very simple algebra. You have only to divide both sides of these equations by m1 m2. Okay, and at the same time you have seen that r is equal to r1 minus r2. So if you will differentiate this equation both sides with respect to t 2 times, then what will be the result? This will be r double dot equal to r1 double dot minus r2 double dot. So you can see in the term in LHS there is r1 double dot minus r2 double dot. And so instead of this r1 double dot minus r2 double dot, now we can write r double dot. Okay, so that has been replaced by r double dot, and in the RHS, in first term there will be only f12 internal, and the remaining term is this. You have already understand it. Okay, now you can see m1 m2 divided by m1 plus m2. This quantity has a dimension of mass, and so we actually represent this mass m1 m2 divided by m1 plus m2 by the symbol mu. Okay, it means mu has been written at the place of m1 m2 divided by m1 plus m2. So mu r double dot equal to f12, this is in fact internal, and plus again here there is m1 m2 over m1 plus m2, so we will again write here mu at times this much, you can see. Okay, now this is actually the equation from where you can see that we can deal with a motion of two body system in terms of motion of a single body system. But how? For this let us assume that the mass m3 which we have considered outside of our system m3. Now let us consider that this mass m3 is far apart from our system. It means this m3 is situated at a very large distance from our system. For example, a practical example, we will also see later on that particular example in detail. If you consider that there is a system of Earth and Moon. You know, Earth and Moon interact with one another via a gravitational force. And at a far distance from Earth and Moon, the Sun is situated. So in this condition, if you consider that the Earth and Moon forms a system, then this Sun may be taken as an outside object. But you know that Sun also exerts force on the Earth, the Sun also exerts force on the Moon. So that will be external forces. But distance of this Sun from the Earth or the Moon is very large. So we consider this particular situation, that when the source of external force, which we have denoted by the symbol m3, is far apart from our system, we consider it. Actually, in that condition, you will see that if we consider that the force exerted by the outside source, that is by the m3 on the masses of our system, that is on m1 and m2, then you will see that if we consider if we consider that the force exerted by the source outside source on the masses are actually proportional to that their mass, then we will get a very simple result. So let us consider. Let us see this figure. We consider that this is our mass m1 and this is our mass m2, and from this m1 and m2 at a far distance there is the mass m3. This is your mass m3. Okay, and this distance these distances are r1 and r2. Okay, r1 and r2, and let us consider that the angle made by these two objects m1 and m2 at the position of m3 is theta. Okay, so in this condition, if we consider that if m3 is far apart from m1 and m2, that is, you can say this distance was r, as you have seen earlier. That is, this r is much smaller than r1, and also this r is much smaller than r2. Okay, in that condition, these r1 and r2 will be almost parallel to one another. In that condition, this theta will tend to 0 and r1 vector will be almost parallel to the r2 vector, and therefore the magnitude of these r1 and r2 will be almost equal. R1 and R2 will be almost equal. Okay, and in this condition, since R1 and R2 will be parallel to one another, so this result implies that F1 external, that is force exerted by M3 on M1, this will be also almost parallel to F2 external. F2 sorry, actually I am suffering from cold and cough, so don't mind it. Okay, almost parallel. Now, as I have told you earlier, that we are considering a particular fact. If F1 external is proportional to M1, okay, and F2 external, that is force exerted by M3 on M2, this is proportional to M2. If we consider like this, or if it is possible, then what will happen? You know, in that condition, F1 external will be equal to a constant times M1, and F2 external will be also equal to the same constant times F2, and therefore you can see from here that F1 external over M1 will be equal to F2 external over M2, and this will be actually equal to constant. Okay, but this is possible only when F1 external is parallel to F2 external, and F1 external and F2 external will be parallel only when the third outside object is far apart from our system. Only then these two forces will be almost in same direction. Okay? And the forces F1 external and F2 external both are proportional to the masses M1 and M2 too. When these two conditions will be satisfied, then F1 external by M1 and F2 external by M2 will be equal. So see, in this condition, when these two conditions will get satisfied, then what will be our equation 3? You can see here. In this equation 3, see the second term in RHS where there is F1 external by M1 minus F2 external by M2. Since in those two conditions, these F1 external by M1 and F2 external by M2 are equal, so these two terms will cancel out. So this second term will vanish in equation 3 in RHS. And in that condition, the equation of motion will be what? That will be simply mu r double dot equal to F12 internal. Okay? So in this condition, hence the equation of motion will be now. What will be the equation of motion? You can see in LHS there was mu r double dot, and in RHS there is F12 internal, and second term vanishes. So you can write now F12 internal is equal to mu r double dot. So you can see this is just equation of motion of a particle whose mass is equal to mu. This is just equivalent to a single particle whose mass is equal to mu, and its position vector is r. Its position vector is r. Okay, or its acceleration is r double dot. So how where this mu will be now considered? How this problem will be reduced to a single body problem? You can now see. Actually, with the help of this equation which I have just obtained here, that is, say this is equation 4, with the help of this equation we can actually reduce the two body problem into a single body problem. Actually, for this, first of all we have to find the position vector, or simply you can say position of the center of mass of the two body system. How we will convert a two body problem into a single body problem? Now you can see what is the working rule, what is the technique. You can see here. See, this was our mass M2 and this was our mass, let us say M1. I am showing those two bodies just like point masses. Okay, and this is the line joining the two masses. Let us see. The position vector of M1 was R1 with respect to the origin O, and that of M2 is R2. So if you want to convert a two body problem into a single body problem, then what we will have to do? See these steps. This is actually the procedure, or you can say the technique, how we can convert a two body problem into a single body problem. So for this, first of all, find the location of the center of mass of this two body system. Let us see, let us consider that this point is the center of mass of the system m1 plus m2, and the position vector of this center of mass is, let us say, RCM. Okay. So if you want to find the, if you want to convert the two body problem into a single body problem, then in first step you have to find the position vector of center of mass with respect to the origin. So let us find first of all RCM. This is your first step. And you have definitely studied in your lower classes the concept of center of mass. So what will be the position vector of center of mass? You can see this will be m1 r1 plus m2 r2 over m1 plus m2. So at first find this position vector RCM. Now let us see. Once you have decided the position of the center of mass, then imagine that the total mass of then imagine that the origin of the coordinate system is not at O, but now consider this is located at the position of the center of mass. It means you have to shift the origin. This is in fact RCM. Okay. Now we will take this center of mass as origin. Okay. And with respect to it, this center of mass, locate a point whose position vector is R. And you have seen R is actually R1 minus R2. So with respect to this center of mass, we locate a point whose position vector with respect to center of mass is R. Okay. And imagine that at this point whose position vector is R with respect to the center of mass, there is a point mass which is equal to mu. It means you have to consider that a point mass whose value is mu, and that mu is equal to m1 m2 divided by m1 plus m2. This mass is located at a point whose position vector is R with respect to the center of mass of our system. Then you have to forget that in our system there was two masses. Now think that there is only one particle in this system, and the mass of that only one particle is mu, and its position vector with respect to center of mass of the system m1 plus m2 is equal to R. Okay. So you have to actually find the position of center of mass, and then with respect to that center of mass, you have to locate a point whose position vector will be R, which is actually equal to R1 minus R2. Okay. And at that point you have to assume a single particle of mass mu. Now write the equation of motion of this single particle and solve it. You will get the result. It means the problem is now writing equation of motion of a single particle whose mass is mu and position vector is R. So its equation of motion will be what? You can see its equation of motion will be simply equal to F12 internal is equal to mu times R double dot. Okay. So in this way you can actually reduce the problem of two body into an equivalent problem of single body. Okay. Okay. Now, once the problem is solved by reducing the two body problem into a single body problem, then again you can determine the individual body's motion. It is also possible. Okay. So the approach of solving central force problem is to first convert a two body problem to a single body problem. Okay. And for solving the single body problem, you have to find R, which is R1 minus R2, and you have also to find RCM, and then with respect to the position of center of mass, you imagine that there is a point mass which is equal to mu, and then you write the equation of motion like this, and the problem gets solved. Okay. So this is the technique how we can actually uh, convert or transform a two body problem under central force into its equivalent single body. Okay. Now in the next lecture we will see that the motion of planets, motion of, or you can say we will deal with the planetary motion. And you know, in case of planetary motion, there is an interaction between the sun and the planet. So that will be a very good example of two body problem. And in all those results, we will actually treat the motion of a particle not of two bodies by reducing the problem into a single body problem. Okay.